Okay, hopefully everybody is having a good semester and staying safe and all that good stuff. So today we talk about Hermite interpolation. So we're building off of what we did in the last video, and also cubic splines. So Hermite is going to allow us to expand the idea from Newton to incorporate derivatives. Newton's interpolary divided difference method to include information on derivatives. Okay, now this is really pretty straightforward, but I'm going to first do a warm-up and we're going to work up to this idea. Okay. Okay, we are going to do actually a warm-up. Find A, B, C, and D such that so we're going to have a cubic and I want f of 0 equals 0, f of 1 equals 0, f prime of 0 equals 1, and f prime of 1 equals negative 1. And you should have been able to do this upon arrival in this class, so I will let you just pause the video and see what you can do with that question. Okay, go ahead, try it. Okay. So I'm assuming that what you did went something like this. Okay, you probably, I'm going to move the question over here so I can put the answer on the other side. I'm going to say, oh, first of all, I'm going to need the derivative. Okay, now f of 0, f prime of 0 is equal to c. So that's 1. And we know, because of this, we know f of 0 is equal to d, so that equals 0. F of 1 is a plus b plus c, and that has to equal 0. What about f prime of 1? Is 3a plus 2b plus c. Did we have any clues about c? We knew c is equal to 1 already, but d we know is 1. F prime of 1 is negative 1. So this we know is 1 also. So now we have two equations and two unknowns. We know b is equal to minus 1 minus a. So 3a plus 2b plus 1 equals negative 1. That's annoying, so I'm going to pause for a second. Okay, so a is 0, b is negative 1, c is 1, and d is 0. So finally we have a is gone, d is gone. What do we say? b is negative 1. And c is 1. Okay, so that's just an example, but remember we have some friends who really don't like algebra and they're sticking up for us. So how would Newton do it? What would Newton do? I'm going to set this up. Okay, so what would Newton do? He would say, well, let's put the x's here, and he would not want to force them to be, let's say, equally spaced or anything, but this is a little bit weird, right? Because we had derivatives, and I haven't brought them into play yet, but what I have done is I've duplicated each point twice. So we had the point 0, 0, and so you get 2 copies of it, and we had the point 1, 0. So why on earth am I making the claim that this is what Newton would do? Well, what we're going to do is here, instead of using the divided differences to get the next column, I'm just going to use f prime at 0, because if I try to just do this, it's going to be 0 over 0, but you understand calculus. That's actually a limit, and this guy is going to be f prime at 1. So instead of actually having an approximation to the derivative, we're going to have the actual derivative there, and then this guy is going to be the usual divided difference, okay? Only wherever, in the middle of wherever your duplicated points are, that is going to tell you where the actual derivative lies, and then in between the steps, divided difference. The usual divided difference goes there. Okay, so let's figure out what the usual divided difference is, and then everything outside there is going to be the usual divided difference. So we're going to put 1 over here, because that's what we were told to put there. That's what we had in our problem up above. Let's just double check. F prime of 0 is 1, f prime of 1 is negative 1, okay? And then we use our usual divided difference, which is just 0, divided by 1 in this case. And then we're going to do the usual game from there on out. So we're going to do, try to get rid of this carefully. Okay, so now I'm going to put negative 1, and 0. And remember, when we do these, we go all the way back to this x and all the way back to this y, which isn't a big deal if you mess up here, because, well, there's not really that many mistakes you can make, but sometimes you can. So just remember where those are coming from. Okay, now let's see. We actually lost our cubic just like before due to the symmetry in the problem. We actually just have a parabola, but we're going to go ahead and write out what we got. What we got here is y equals, and where are the special values that we're tracing, right? 0 plus 1 times x minus 0 minus 1 times, and here's the thing, you have 2x equals 0, so you're going to use 2 of them, and we didn't use our last term. If we had our last term, it would have been x minus 0, and then x minus 1, okay? So we didn't use it because it's 0 times this, so we don't have to write it in. Okay, and if you work that all out, you just get x minus x squared, okay, which is pretty much what we just got. Let's just check. It is, in fact, exactly what we just got. Okay. So which should be better? What do you think? Using 4 points or using 2 points with their derivatives? So this is a question for you. Question, which is better, and what do you mean by better? Using n points with their derivatives, or just using 2n points? I don't really have an answer for you, but it really depends on the situation, and there's many times where you'd like more control in fewer places. So if what you want is more control but in fewer places, then this is what you'd do. Now, polynomials wiggle a lot, so maybe just using 2n points isn't such a bad idea. So what I'm going to do is I'm going to say, like, what if, for this same problem we just did, what if instead we have the point 0, 0, and we're not allowed to duplicate it and use this Hermite thing. We can do 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Those are supposed to be the same. Let me count how many zeros. 7 zeros. 1, 2, 3, 1, 2, 3, and a 7th zero. Like, let's use this point instead of defining the derivative to be 1 there, and then we'll use this point, and again, instead of defining a derivative to be -1, we could have said, we could have done something like this, and then we would do like something like this. That's supposed to be giving you, let me count those 9s, I want to be sure that's right. We have 7 of them, and then we should have 7 zeros. I'm always afraid I'm giving the wrong number. Do I have, that's the 7th position. 1, 2, 3, 1, 2, 3. I think I'm off by 1. That's supposed to give you a slope of -1 there. Okay, so if you did that instead of what we just did, you would get pretty much the same exact result, but it would be off by a smidge. As an exercise, you can go ahead and work that out and find out what you get. And if you were to instead write it like this, if you were to write the points as, I hate when the pen doesn't come up for me, 0, 0, epsilon, epsilon, 1, 0, 1 minus epsilon, and hold on, and epsilon. There we go. If you did all the calculations just using that, then let the limit as epsilon goes to 0, then you take the limit as epsilon goes to 0, then you'll still end up with y is x minus x squared. So that's a fun exercise for you to do as you're going over these slides. Okay? Next I'm going to go into cubic splines. Do not call them spleens. Apparently some people call them cubic spleens, but spleens are organs of the body. These are splines. It rhymes with lines.
No, I didn't think of it. You have to start like this with your feet on the ground.
Okay. Okay. Now, there's 2 flavors, free and clamped, and we'll talk about both.
You have to start over again.
Okay, so there's 2 flavors,
Okay,
and we'll talk about both.
very close to the ground.
So what you want to imagine is a whole bunch of cubic interpolary functions connected end to end. And the whole thing is just S, but we're going to break it up into S1, S2, S0, S3, and in the very last one, whatever it is, however many there are. Okay? So the whole thing, whole deal, is just called S of x. That's for the spline. Okay? N pieces. In this case, n is 7. Okay? So cubic splines, piecewise cubic polynomial. So this is a piecewise cubic polynomial. All right. So overall, the spline has to interpolate points in given locations. All right, so for example, these points have to match. And because they match, so for example, these 2 points here, okay, this guy and this guy have to be members of S0, and like these 2 guys have to be members of S4. So by virtue of that, S0 and S1 are going to connect together. Okay, so they're going to match, and they're going to match at that designated point. Now, additionally, you also, so the way we write this is we would say S of xj is f of xj. So it matches the provided points. So there's already now 2 conditions per segment. Now, a single derivative everywhere matches. So for example, what this means is on the join points, if you have a join point right here, and this is Sn, and this is, say, Sn plus 1, at the join, we have a smooth derivative. Well, in other words, we have a derivative. So Sn at, let's make it point x, so the derivative has to equal, those two derivatives have to be equal so that they can do that, okay? So imagine if you're putting like a drinking straw around a flexible piece of metal. So you have some kind of flexible piece of metal and another flexible piece of metal, and you're putting some sort of drinking straw or some kind of plastic tubing of some sort around the two ends of the metal. That's what you kind of want to think of, like a semi-rigid tube. And this, you can make a physical object that essentially simulates this, so that these two ends are not only meeting, which you could do with a piece of tape, but then they would be kind of, there could be a corner there. So you put some kind of tubing around it so that the two ends butt up against each other and they have to kind of share a derivative there. Okay? You could also put like you could put a nail right there inside the semi-rigid tube, and you could nail it into the board so that the point matches, and so by this construction you could force the point to match the required function, and then because you have like a piece of tubing around the two ends like that, then you essentially force the derivative to match there also. So that's kind of like something you can imagine. Okay, so you have two options. You have something called free and something called clamped. Okay, and so you have still 2 degrees of freedom remain. So what are you going to do with your 2 degrees of freedom? And those choices are going to be different. The answer to this question is going to differ based on whether you've picked a free or a clamped cubic spline. So everything in the middle will be the same. All right, so if you want the two outside derivatives, the second derivatives to be 0, so we don't normally care about the second derivative, but this is an exception, okay? So we can ask, then we would have a free cubic spline if we decide to ask the second derivative on the ends, on the two outside ends, to be equal to 0. Okay? So that's one option. The other thing you can do is a clamped cubic spline, and so what happens here is you're saying, you know what, I just want to match the derivative of the original function. So previously we only required the two ends, like when we were meeting. Let me just finish writing this, and I guess I'll go back up to the other one. Previously we only asked these guys to match each other. So it didn't necessarily match the original function, but they had to match each other. So that's kind of a little subtle difference. Here we're saying, I don't know, we have 2 degrees of freedom left. What are we going to do with it? Well, we could just ask the endpoints to match the derivative that the original function had there. And that would actually require you to know the derivative of the original function at that point. Because otherwise, if you don't have any extra samples, you're just going to do something less useful by just, I guess, estimating somehow. So if you don't know what the derivative of f is there, you might just prefer a free cubic spline, or there may be some other reason why you prefer. Okay, so you can choose the two outside derivatives. Okay, so those are two choices you have. You know, maybe you'll get lucky. Hint, hint, think about your homework. Maybe you'll just get lucky. Maybe all of this will be satisfied. That would be interesting. It's possible. But you can only exert a certain amount of control, and the rest of whatever happens is just the luck of the draw. Okay? And that is the end of what I have to say about that. Hope you have fun with your worksheet.